Hello. Okay. Yeah, section 3.3, relations. So here we need to establish some mostly definitions regarding relations. So what is a relation? Okay. So a relation from one set to another, right, can be thought of as a table that lists the elements of the first and if that are related. So for example, a relation of students to courses, you could have like Bill is in computer science. Mary is in math. Bill is in art. So Beth is in history. Beth is in computer science. Dave is in math. Notice that here we have the same Bill uh, being corresponding to two different things. So it's not necessarily a function from the set of students of the course. In fact, in general, it's not. It's just a relation. It just talks about whether one thing is related to the other. Okay. So here's a definition. A binary relation, right, R from a set X to a set Y is a subset of the Cartesian product X cross Y. So yeah, it's just a subset. That's so, X, Y is in R. We write X is related to Y and say that, well, X is related to Y. If X equals Y, we call R a binary relation on X. Okay. So yeah, we're going to develop some essentially some different types of properties of relations. Okay, let's look at this example. So here, let's let X equal 2, 3, 4, and Y is equal to this set, right? If we define the relation R from X to Y by X, Y is in R, if X divides Y, okay, then you can notice it will, let's see, 2 divides 4, 2 divides 6, 3 divides 3, 3 divides 6, and 4 divides 4. So that would be our relation. Okay? So it just talks about when two things are related. Okay? Let's take a look at this one. Here's another example. Let R be the relation on X. So you have these numbers 1, 2, 3, 4, right? Let R be a relation on this set defined by X, Y is in R. If X is less than or equal to Y, and X and Y are in X, then the relation, right, here it is. We have 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, 4, 4, because look, we're just looking to find out when is X less than or equal to Y. You can kind of see this here. I think that's what this diagram has to do. Is, let's see, is that different? 1, 2, 3, 1, 4. Yeah, I guess an informative way to picture a relation on a set is to draw a what's called a digraph. Okay, so yeah, it's kind of important. We'll go over this right now. So for example, let's take a look at this one. So here we see that 1 is related to itself, 1 is related to 2, 1 is related to 4, 1 is related to 3. 2 is related to itself, 2 is related to 3, 2 is related to 4. See how that's working? So there we have it. Let's see. Example. The relation R on A, B, C, D graphed by this digraph in figure 3.3 is R equals A. See, A is related to A. B is related to C. B is related to C. C is related to B. C is related to B. And D is related to D. So this is a way of drawing a picture of that relation. Okay, another definition. Okay, so some properties of relations. The idea of being reflexive. So a relation R on a set X is reflexive if X is related to X, right? If X is related to X, right? For every X in X. So I guess, yeah, that's what it is. It seems strange, but that's a reflexive. It's the definition. Let's take a look at this example here right now. The relation R on X, 1, 2, 3, 4, defined by X, Y is in R. If X is less than or equal to Y, for X and Y and X, is reflexive because we have equality, right? 1 is less than or equal to 1, 2 is less than or equal to 2, 3 is less than or equal to 3, 4 is less than or equal to 4. So this is a reflexive relation. Okay. Next definition. A relation R on a set X is symmetric if for every X and Y in X, if XY is in R, then YX is in R. Okay, so for symmetric, you can see that. Let's take a look at this one up here that we just looked at. So let's look at this relation, the relation of less than. This is not symmetric because clearly 1 is less than or equal to 2, but 2 is not less than or equal to 1. So this relation here is not symmetric. Okay, let's see what this is. There's another example. Let's look at this example. The relation R, A, B, C, C, B, D, D. Well, yeah, on X. This is symmetric because take a look. Anytime you see BC, you see CB, DD, AA, right? So it's symmetric. Okay. Here's another one. So definition, really important. A relation R on a set X is anti-symmetric if for all X and Y in X, if XY is in R and YX is in R, then X equals Y. That's just very strange, very strange kind of condition it looks like at first, but this turns out to be a critical definition. Right? Let's look at this example. The relation R on X equals 1, 2, 3, 4 divided by XY is in R if X is less than or equal to Y. Okay, let's take a look at that one. This is antisymmetric because for all X and Y, if XY is in R, right, i.e. X is less than or equal, and YX is in R, right, well, then the only way that happens is if they're equal, right? So, so that's this is an anti-symmetric relation. Let's see, what else do I want to talk about here? Mostly this is a bunch of definitions. This is a critically important one here. A relation R on a set X is transitive, right? If for all X, Y, and Z, right? If X is related to Y and if Y is related to Z, then X is related to Z in R, okay? Let's see, let's take a look at this example. The relation R on X equals 1, 2, 3, 4 divided by X, Y is in R if X is less than or equal to Y for X, Y, and X is transitive, right? Because X, Y, and Z, if X is less than or equal to Y, I'll read it in terms of our relation. We know that if X is less than or equal to Y and Y is less than or equal to Z, we know that X is less than or equal to Z, and where R are the real numbers, okay? All right, let's take a look at the this last thing here, the definition of a partial order, okay? So a relation R on a set X is a partial order if R is reflexive, antisymmetric, and transitive. All right, and that's the idea of a partial order, okay? I'll let you go through the rest of the examples, but yeah, get familiar with the definitions, right? And here's our last one, I guess. Definition, let R be a relation from X to Y. The inverse relation R, denoted by R inverse, is a relation from Y to X defined by, we get R inverse is equal to the set of all YX where XY is in R, okay? So essentially, here's a good example. If you have R, the way you get R inverse is just turn all the elements around, right? 2, 4, 4, 2, 2, 6, 6, 2, et cetera, et cetera, et cetera. And okay, that should get you ready to do your problems in section 3.3. Okay, thanks.